Bismillahirrahmanirrahim. Welcome to the 16th lecture of Statistics and Probability Theory. In previous lecture, we have studied Poisson distribution. Poisson distribution has the probability mass function, which is P of x, where x is the random variable, is equal to e raised to power minus lambda into t, where lambda is the average number of occurrences of the event, t is the time in which the average number of outcomes are calculated, and this one is lambda into t raised to power x over x factorial, and x is equal to 0, 1, up to so on. So this is the basically distribution of the rare events. The events that occur rarely, for example, a number of earthquakes occur in some particular year, number of calls arriving at the switchboard in a particular time. So all these are the events which are in a particular or fixed time span, and this is basically the distribution for the rare event. We will continue with this topic, Poisson distribution, mean and variance and standard deviation of Poisson distribution. One of the unique characteristics of Poisson distribution is that its mean and variance are same. Mean, which we usually denote with the Greek letter mu, is equal to lambda into t, and variance is also equal to lambda into t, whereas standard deviation is equal to under root lambda into t. So this one is the unique characteristics of the Poisson distribution, that its mean and variance is same. Approximation of binomial distribution by a Poisson distribution. If you recall from the previous lecture that binomial distribution has two parameters, n and p, where n is the number of trials or number of times experiment is performed, and p is the probability of success. Binomial distribution has four properties. The very first property was there are two possible outcomes, which we usually categorized as success and failure, and success is denoted by p. Number of trials is fixed, which we denote by n. All successive trials are independent, and probability of success remains constant from trial to trial. So this is the probability mass function of the binomial distribution, and whenever the number of trials in a binomial distribution becomes very large, and the probability of success becomes very small. This one is written n approaches to infinity. It means that n becomes very large, and p approaches to 0. It means that p is very, very, very small. So you can approximate binomial distribution to the Poisson distribution with parameter mu. So this is the approximation of binomial distribution to Poisson distribution, that whenever we have n very large and p very small, binomial distribution with two parameters n and p will tend to Poisson distribution with parameter mu. This one is the probability mass function of the probability distribution of the Poisson distribution with parameter mu. So, x approaches to binomial with parameter n and p, then n can reasonably be approximated by a Poisson distribution with mean np if n is large and p is small. This np is basically equal to mu, which is basically the mean of the binomial distribution. Mu is equal to n into p, where n is large and p is small. It is sometimes convenient to approximate a binomial distribution with a Poisson distribution because it is slightly easier to calculate probabilities using a Poisson distribution. Two frequently used rules of thumb are that when you will approximate binomial distribution to Poisson distribution, whenever n is greater than 50 and n into p is less than 5, or n is greater than 50 and p less than 0.1. So it is convenient to use Poisson distribution instead of binomial distribution whenever n is very large and p is very small. So if x be a binomial random variable with probability distribution and the parameters n and p, when n becomes very large and p becomes very small, so the mean of the binomial distribution, which is n into p, is mu, remains constant. So then the binomial distribution will tend to Poisson distribution. So this is the probability mass function of the Poisson distribution, which is approximated from the binomial distribution, and the conditions are that n is very large and p is very small. So this one mu is basically the mean of the binomial distribution, which is n into p. This, as we are seeing that n becomes very large, it means number of trials are increasing, and we are seeing that p is very small. It means that probability of success is very, very small. So it means that our outcome of the chances of outcome of our interest in an experiment is very low, or it's very minimum. So this means that on average the occurrence of that particular event in this much trial will be very minimum and mean will be constant. So that's why binomial distribution is approximated to Poisson distribution with the parameter mu, where mu is the mean of binomial distribution and x is the number of observed successes as it is defined earlier